Okay, good morning. I'm sorry for the delay. So we'll discuss pumping lemma. We'll continue our discussion on pumping lemma today. So we have seen what pumping lemma is for context-free language. So just to recap, uh, this is the pumping lemma, right? So if A is a context-free language, then there is a natural number P, also known as pumping length, where if S is any string in A of length at least P, then S may be divided into 5 parts, which is U, P, X, Y, and Z, satisfying the following conditions. Right? Condition number 1 is for all values of I greater than or equal to 0, right? So greater than or equal to, so equal to 0, U followed by I copies of P, followed by X, followed by I copies of Y, followed by G, belongs to A. Right? So this is called pumping. So and when I is 0, uh, you that means if when I is 0, then you also can say that U, X, and G also belongs to A. Then we have the second condition is the length of by is greater than 0 or it's non-zero. So length of by, that means either p contains something or y contains something or both by. The third is bxy. The length of the bxy is most p, right? It cannot be greater than p. And in the last lecture, we have also seen something like 0 power n, 1 power n, 2 power n is not a context-free language, and we have proved it using pumping lemma. So we started proving pumping lemma last time, and in between we stopped. Let's look into that proof again. Yeah. So let's look into this proof. So what we said is we started with a grammar, which is a context-free grammar for language L, right? So we started with a grammar which is context-free language. That G contains M non-terminals, right? Non-terminal variables, or you can always say M variables. So if it contains M variables, we'll construct a parse tree out of a parse tree T for G after converting it to CNF. And when we convert it to CNF, it is guaranteed to be the parse tree is guaranteed to be a binary tree, right? So parse tree is guaranteed to be binary tree because it's a CNF, a Chomsky normal form, and the height of the tree, let's say, is M plus 2, right? So if it is M plus 2, then the string length, string will always be nothing but the leaf nodes, right? So only the leaf nodes will be the terminal because all the other nodes will be non-terminal. So let's say the length of S is less or equal to, so this means the height of the tree is M plus 2, then the length of a string is less than or equal to the power M plus 2. So we also asked like how many non-terminals will be there in the longest path. So the height is M plus 2, right? Since height is M plus 2, that means M plus 1 non-terminals will be there because the last one will be anyway terminal, right? So last one will be anyway terminal and all this will be non-terminal. Then we argued that, okay, so you are saying that there are M plus 1 non-terminals in this path, right? So in this path, there are M plus 1 non-terminals, but you just said that there are only M non-terminals, right? So this is what we assume, that there are only M non-terminals. That also means that some of the, at least one of the non-terminal variable or one of the variable is repeating in this sequence, right? And then we said, okay, let's say that A is the variable which is repeating, right? So A is appearing first time here and second time here. So let's say you are going from leaf to root. First time A is here, second time A is here. Let's say that's the condition, right? So S produces U, A, and G, right? So if, this is what S. So S. So this symbol means that uh, if you apply as some rules, some set of rules, you will come up with something like U, P, X, Y, G, right? As by applying multiple rules, S will lead to U, P, X, Y, and G, right? So S is leading to U, P, X, Y, and G. A leads to X, right? So this is very clear that A leads to X, and A also leads to BXY. A also leads to BXY. Similarly, S also leads to UAJ, UA, right? U, A, and G. And the last one is A leads to BAY. A leads to B, and then A, and then Y, right? So these are the set of rules now, and from these rules now one can easily find out that the first condition of the pumping lemma, that is, what I can do is I can apply this S equal to S implies UAZ. Now that also means that I can apply just a minute. So this is U, V, A, Y, and G, right? And V is nothing but, so this one, this A is actually U, V, this one, V, X, Y, V, X, Y, Y, G, right? This is how I have just produced that U, V square, X, Y square, G. And you can see that it's not very hard to actually produce all the strings like U, P cube, P power 3, X, Y power 3G is also easy to produce from this set of rules, right? And this is what is the first condition is, right? So the first condition also says that your the first condition, if you look into, let's look into the first condition. So UXG also belongs to A, right? UXG also belongs to A. How will that happen? U, V, and Y has to be null, right? So UXG, right? So just a minute. So yeah, A is A itself, right? So if I apply this rule, so if I apply this one and this one, right? So then S will also imply, S can imply U A G, and that also implies U X G, right? U X G. So this is also possible for I equal to 0. Also, it is possible. What do you mean by U P X Y G? That you can anyway produce, no? If you replace A with X, U B X Y G, right? If you replace this particular A, let me, this particular A with X, you can produce. Now, what is the question? A is different in both. It is not really different. So it can be like it's like so. If you remember when your formula, if you remember your CNF formula, right, or any context-free grammar, usually what happens is something like this is what you write, right? So A implies, let's say, X A, right? So here the similar thing is happening, right? So these two A's are driving two different things. It looks like they are driving two different things, but that is because that's how it is defined. One is represented CFL. Here A is non-terminal. Oh, okay. Sorry. So let's write the first one as L. Okay. So what actually this question is this A. Let's say okay. Yeah. That's good. So this is, let's call it L. To avoid confusion. Okay. To avoid confusion, let's call it L. This has nothing to do with that A. That A is a variable. Okay, so this particular A is a variable. That's not a language. And this you can simply now you can see that the first condition, which is u p power I x y power I g, also belongs to this particular language, right? A. Sorry, L. That is easy too. So now, what is the next condition? The length of Py cannot be empty. How do you show that? That is also easy to show, because if length of Py is empty, then A will be only producing X, right? A will be producing X. So that is not the case, because you are producing a UXY. So that is that way you can show. And the third one is the length of PXY is less than PR. So that I'm leaving to you. Yeah, then both. And the third condition, I'm leaving what is the pumping length. You should look into the book and prove that what is the pumping length in this, and in this particular proof, and also how do you prove the third condition? Okay, sure. That's let's do that from using book. Okay, so any question on pumping lemma? Like, sorry. Sure. Now, yeah, so some like you should definitely go through the book to understand like how to write technical, like formally this proof, right? Because I have just given the proof idea, but you can actually look into the book and understand how do you write the proof formally, right? Uh, okay, so one more interesting thing which I want to cover today is CFG2, CFG2. Please solve the question of previous practice set of for pumping lemma. Which is which previous set? This is pumping lemma for regular. Okay. So we will do that. Not today, but maybe I will see which question. If you can point out the question number, that will be good. Can do that. Right. So stone automation. Yeah, this one. And we'll do question number 10. Okay, thanks. So we'll do that sometime. Okay, so today another thing which I want to see is let's say you have a grammar given, right? So if you have a grammar given, or let's call it CFG given, can you convert it to PDA? right? Because we know that those two things are equivalent. If it is a context-free grammar, you can always design a PDA for that, right? So and the vice versa as well. Can we do this, right? So there is some set of rules for doing this. So you remember that PDA also has a stack. So to convert a context-free grammar into PDA, these are the steps. The step one is push dollar and start symbol, or let's call it start variable on the stack. Okay, so this is the first thing. You push dollar and the start. So what is given? We have some grammar given, and this grammar we want to convert it to uh, PDA, right? So what we will do is we'll push this dollar and the starts variable on the stack. Now, second thing is repeat the following step. Repeat the following steps. Let's call it 2.1. If the top of the stack is a variable symbol, if the top of the stack is variable, right? So variable means it's not a start variable. When you are saying variable A, let's say, then non-deterministically choose one of the rules of A, and push onto the stack. Right? Whatever we will see the example when it will be more clear. So push on the stack from the from right hand side, so that we will see what does it mean. So 2.2, let's call it from RHS. Second 2.2 is like the top of the stack is a terminal, let's say, right? So this is tricky. So if the top of the stack is, let's call it A, right? Terminal is small a. Then read the next symbol from the input and compare it with the A. Read the next symbol from the input and compare it with A. If both are same, right? If both are same, then pop, right? So if they both match, then if both are same, then repeat. Keep on reading this A's and just repeat it, right? And if they do not, if they do not match, go to reject state. Go to reject state. All right. And the last condition, last stage is 2.3. If the top of the stack is, if top of the stack is dollar, right? If top of the stack is dollar, then enter accept. right? Then enter the accept state, and doing so accepts the input if it has all been read, right? So we'll see like that. So we'll see the example. So this is basically what we are doing. So we have a grammar given, and we are going to convert that to PDA. So let's first see an example to understand it better. Like whatever we have just said. So let's take an example. So let's say the grammar is S implies A, T, B, B, and T implies TA null. This grammar is given, and our task is to convert this to PDA, right? The push down automation. So according to rule, the first thing we will do is, of course, we'll have a start state, right? So we'll have a start state. Let's call it Q start. So we have a start state, which is Q start. Now, what we will do is, according to our rule, we have a stack, right? So in the stack, we are going to push dollar, right? So we push dollar in the stack and change the state, obviously, because without reading anything, you push dollar and go to Q1. And then you again push start symbol, right? So you push start symbol, go to Q2. Everyone is okay with so far? So what we have done is just did the first step of our procedure. The first step of the procedure is push dollar and start variable onto the stack, right? So we have pushed it, and we have without reading anything in the symbol, we have done so far. Now Q2 has to be looping state, right? Q2 will have some loops. Why? Because they repeat the following step. So Q2 has to be loop. So in Q2, what are the things can happen? In Q2, if the top of the stack is variable A, if the top of the stack is a symbol, right? And the third is if the top of the stack is dollar, right? So top of the stack can be either of these three things. What are the three things? Top of the stack can be either a variable, like it can be a symbol, or it can be a, right, it can be a dollar. So these are the three things it is possible. So now what we will do is we will see the see what it is, right? So if it is let's say a variable, if it is a variable, then we will push the right hand side of this rule, right? So we will push. So what we will do is, if I read, let's say S, okay, because here it is S. So let's say what will happen there is as follows. The multiple things will happen here. I will write it here. So first thing is, without reading anything, I will replace S with B, and without reading anything, I will replace without B to T, and without reading anything, replace A. So what we are doing is, we are replacing this rule, right? So S has what are the rules for S? There are two rules for S. One rule is S implies ATB. So instead of ATB, we will from the right hand side to right to left we will read. So what we will do is, we will replace S to B, and epsilon to T, and epsilon to A. All right. So BTA. Okay. So what we are pushing is B. So that is the order. We push B, then we push T, then we push A. And that is important to have that reverse order, because because of this stack operation. it's possible that your start symbol is so because we have two rules for S, right? We have two rules for S. Another rule is S implies B. We can also do that. We can also do S implies B. So if it is, yeah, so only B. If it is only B, then without reading anything, right? We will replace S with B. Without reading anything, we will replace S with B. So this is done with if the your top of the stack is S. If your top of the stack is T, what will happen? Again, there are two rules. There is rule number one, rule number two. If I apply rule number one, you guys can tell me what should happen. What should I push first? Without reading anything, I should replace T with A, right? I should replace T with A, and then without reading anything, I should replace epsilon with T. All right, so this is again in the reverse order. We push first A, then push T, and there is another possibility that you choose the epsilon rule. So if you choose epsilon rule, you will push epsilon. Sorry, you will replace T with epsilon. Right? So these are the rules which is possible, and this you will keep repeating. And then when you keep repeating all this, right, there is another possibility is left here. Is you read a symbol in the top, right? There is another possibility is you read either A or B in the top, right? You can either read A or you can read B in the top. That is also another possibility. So if that is there, then we can write, if I read A in my string, and if it is A, I will erase A, and if it is B, it is B, I'll erase B, and then I will go to final state by reading dollar. So this much, right? So this is just very simple. Then this will like two stage procedure actually. If you see, first thing is you are pushing dollar and this is the start symbol, and then you are checking what is in the top. If the top one is a variable, then push the right hand side. Push the right hand side, and if the top one is a non-terminal, sorry, terminal, then erase it or pop them, and while popping all of them and matching them with the original string which you are processing, if they all up match, and then if you finish everything, then if dollar is left in the uh, stack, then you erase that dollar as well and reach to the final state. Okay, and let's take the one example to how to just execute this. Any question?
Sir,
Yes.
sir, when we are writing this at Q2 state, epsilon comma S arrow B.
Hmm.
So sir, it will check whether S is the top of the stack and then pop it and then push B. But sir,
Yes. Yes.
but sir, why we want to pop S? We only need to push B only.
No, no, no. So we are replacing, right? So actually, S will not no more be there, right? So when you do so when you apply this tool, S A T B, right? When you apply this rule, S is no more there. So S should not be there in the stack as well. So you should erase S, and because you are replacing this with this particular rule, right? So instead of S,
Yes, sir.
S, right? Let's take an
Yes, sir.
example. Okay. So let's take an example to understand it, what we are saying. So let's say my string is Okay, so what can this guy produce actually? So this can produce ATB. Let's first look into that. So this can produce ATB, and then T can produce TA, and then this T can be null. This A is A, and this B is B. So this can produce AAB, right? AAB it can produce. Okay, let's look into that. How will it produce? Let's say your string is AAB. Okay, by reading this string, this particular PDA which we have just designed, should reach to the final state, right? If it is doing so, we are okay. It should reach to the final state because AAB is the length string which is generated from the this grammar. Okay, how will we do? First stage, we have a stack which is empty. We are at Q start, and in Q start, without reading anything, we will push dollar. Okay, so let's do that. Right, so this is the string which we are reading. This is the string which we are reading, and so far we have not read anything, and we push the stack dollar. Then Q1, without reading anything, push to the S to the stack. So we will push S to the stack. Fine. So we have done this two push operation. Now second thing is we are in the Q2 state. In the Q2 state, we will pop, right? We will first pop S. So what we can pop is S, right? So we pop means we read. So if the S is there, so now S has to be replaced with some symbol, right? So what we do, we replace it with ATB. Okay. If we replace it with ATB, so S will be replaced with B, right? BTA T A BTA, right? So this is what I am doing. This is what I am doing. I am pushing B, I am pushing T, and I am pushing A. All right. Now, what is in the top? What is in the top of the stack? A. So which rule I should apply? I should read one of the A in my string and erase A, right? So that's what we are going to do. I will read this A, right? I will read this A, and I will erase this A, right? Which rule? This rule. We can replace. We have only two rules. One is T implies TA, and the other one is T implies null. So we will replace it with T implies TA. So what we will do is we will follow these rules. Okay, and then what we can do is T will be replaced with A, right? And this T will be replaced AT, right? So T is replaced with AT. Now, what is in the top of the stack? T, which is a variable, and this T has to be replaced with some rule. So what are the possible rules? There are only two possible rules. One is T implies TA, another one is T implies null. We will replace T implies null. So what we will do is erase this. Done. Now, what is there in the top of the stack? A. What is there in the string? A. Right. So this one I will erase, and this one I will. This A I will read, and this A I will erase. Which rule we are doing? We are doing this particular rule. This particular rule. Now, second thing is what is in the top of stack? B, which is again a symbol. So we will go to the string and see whether B is there in the string or not. B is there in the string. So B is there in the string. So I will read that B and read that B and erase this B. Right? Which rule? This rule. B, read the B and erase the B. All right. And then what is in the top of stack? Dollar. What is in the string? What is in the string? Empty, right? String is already we have read. Nothing is there in the string. So then we can follow this particular path without reading anything. Dollar will be erased. Dollar will be erased, and you reach to the final stage. All right, right? So this is an exercise for you guys. If I ask you to do something like S A B B A B B, it will do. But A B B, will it do? No, it should not. S A B B, it should not recognize, right? So this should not go to the final state. This should not go to the final state. But there can be more example where like there are, so A B. This should go to the final state, right? This should it go to the final state? Yeah. This should go to the final state. So you can check all, you can do the dry run of this ABB and AAB, and what will be in the stack, and what will not be in the stack. All right. So you can try doing this dry run of this PDA. So this is how you convert to a grammar to a PDA, right? So especially the CFG to a PDA. Okay. So how much time we have? Okay, we have some time. Good. So any question on this conversion?
Sir,
Yes.
sir, I have one doubt regarding the convention we followed in this PDA. Like, if we want to do, okay, if the top of the stack is A, then without popping it, push B. So how do we? So can we do that? A arrow A B
No, can you say that again?
means if you want to do that, if the top of the stack is A and the incoming symbol is B, so without popping A, push B.
Okay, so incoming symbol is B. The string contains B. Okay, so
Yes,
this
sir.
is what you write. And what you want?
And
A.
we want to check if the stack top is A and without popping A, push B.
Okay, you want to push B without. Okay. So in that case, you may not. You may have to do like A implies AB.
Yes, sir, that's what I'm asking. Means we can write A B in this place.
Yeah, you can do that, or otherwise you have to write two statements like A implies A, and then so you can also write this way: A implies A, and then the B implies B.
Okay, sir. Okay, sir. And sir, similarly, we can also do that in the left hand side. Means if there is A, we can also write AA. Means if the top of the stack is AA, then push, then without popping it, push B. We can also do AA arrow B.
Yeah. You can
Okay,
do that.
okay,
Yeah. Fine.
okay.
So now let's move to something which is we discussed previously, which is NPDA and PDA. NPDA and DPDA. NPDA and DPDA. Non-deterministic push down or there is a comment here, then the string is not valid. Which string? The NPDA is non-deterministic push down automation, and DPDA is deterministic push down automation. So we have also seen NFA and DFA. Okay, we have seen NFA and DFA, and we have said that they are equivalent. NFA and DFA are equivalent, but NPDA and DPDA are not equivalent. Okay, they are not equivalent. So what we have seen in the definition of PDA few class back, right? So few class back we have seen a definition of PDA. That definition is actually of NPDA. So when we say PDA, we usually mean NPDA, right? When we say PDA, we usually mean NPDA because in NPDA, there is null transition as anyway allowed, and then there are multiple options, right? So it just what we have designed is also NPDA. Why NPDA? Because there are multiple rules, which one to choose is kind of non-deterministic here, right? But DPDA, on the other hand, is deterministic in nature, but it also contains null transitions, right? The null transitions it contains because you have that option that you don't push anything, right? So what do I mean by that? Is the epsilon stack move, right? So epsilon moves takes two forms: the epsilon input moves and epsilon stack moves. So epsilon moves are fine in the DPDA, but it is deterministic in nature, and so the only difference is in this case PDA the transition function del, right? So transition function is the difference. So what is the transition function in PDA? So this is what the transition function is. PDA and NPDA are same. Okay. So just a minute. I think I need some charge. Just give me a minute. Okay, so maybe by the time we can do a small quiz, which is designed for today, class participation quiz, very quickly. So let me share the screen. This is in Slido. Hope you can see the screen. Yes. Please note down this grammar in your paper pen or capture it somewhere, like so that you, because the questions, next 2 3 questions are based on this particular grammar. So either you note it down or you take a picture of it so that you can answer, right? So this is a grammar which is context-free grammar which is given to you, and there will be 2 3 questions based on this. All right, so I hope everyone is noting down either or taking a picture of it. I'll wait for half a minute. Okay, so now join the quiz using this code 195141 slido.com. S is the start state. No, R is the start state. R is the start state. Okay, please join. All right. So here's the question. How many variables are there in G? only 3% are correct, but there are 27% wrong. No? So so variables A and B, the small a, small b are not variable, right? Because they are terminals. Terminals are not variable; they are constant. The other variables like the capital ones, whatever S, R, X, and such things are variables. So the answer is 4. Uh, okay, here we go. Next, get ready. And out of 9 rules in G, how many are not in CNF? Means how many are invalid according to CNF? Seven. Majority is going wrong. Why? Means is there any issue? We can check it. Uh, Last question. No, sorry. Yeah. What describes LG? Language corresponding to grammar G. Madam, palindromes, non-palindromes. Okay. Okay, so let's see, like maybe we can discuss this, all this can discuss in the next class. T implies, T can generate T. Is this true or false? It is false. You cannot generate T with T. All right, so people are making mistake. So we will do this in the next class. All these maybe some corrections may required. We can do that, and in the next class we will also discuss PDA, NPDA, sorry, NPDA, DPDA, and there was one doubt on pumping lemma, so we can maybe try to do that. So next lecture we will be finishing this context-free language, and from Friday onwards, so Friday onwards, we will be doing a Turing machine, right? So which is the second last topic of this course. Turing machine, we will be spending 3-4 lectures, and then a couple of lectures on the remaining thing. Okay, so let's meet on Thursday then, and we can discuss all this on that day, right? Thanks.